Okay. So I understand it has been a long day for everybody. So I wish I could say I would go easy on you. But unfortunately, this lecture is probably going to be the most intense of all of my lectures. So in case you were hoping to have some easy time now, I have to disappoint you. Okay. So to make up for this, I think we're going to do one of the nicest or most important calculations in all of theoretical physics. Okay. So it's going to be a little bit of hard work, but I hope it's going to be worth it. And so in particular, what I want to do today is switch gears. Okay, we're going to start part 2 of these lectures. So far, we have been talking about relics from the hot Big Bang, very light particles that are produced by thermal equilibrium in the early universe. Now we want to talk about relics produced during inflation. These particles are produced by the rapid expansion of the spacetime during inflation. And so in particular, one famous fact about inflation is that any massless particle, quantum fluctuations in any massless particle, get amplified by the expansion of the universe. Okay. Then you can ask, what massless particles do we expect during inflation? And in fact, there are 2 massless particles that are guaranteed to exist in any inflationary model that you can consider. One massless particle is the curvature perturbation zeta. Okay. That particle exists just by the nature that inflation is a time-dependent background, and a time-dependent background had a Goldstone mode associated with it that is massless, and that's what we identify with the curvature perturbation zeta in a certain gauge. So that has to exist. And a second massless particle that has to exist in any inflationary model is the graviton. Okay. So there's zeta and gamma ij existing as massless particles, and we should consider quantum fluctuations in these massless fields and the correlations in the quantum fluctuations in these fields. Of course, we have already discussed how fluctuations in zeta ultimately became fluctuations in the cosmic microwave background. So arguably, we have in fact seen evidence for those quantum fluctuations already. And of course, famously, we have not seen evidence yet for fluctuations in the graviton. But as I will discuss, there are future experiments that measure the polarization of the cosmic microwave background that hope to see signatures of gravitons as well. Okay. In addition to that, and that we're going to be discussing in the next lecture, inflation is also very efficient at exciting massive states. Okay? Because what we consider a light state during inflation has to be measured relative to the expansion rate during inflation, which can be enormous. Okay? So the Hubble rate during inflation can be as high as 10 to the 14 GeV. And so any particle that's much lighter than 10 to the 14 GeV is effectively considered massless or very light. And so those particles will also be excited. And even particles that are a little bit more massive than the inflationary Hubble scale will get excited, and we can look for the imprints of these massive particles. So inflation is a collider that produces extremely high and extremely massive and heavy states. And so it gives us access in principle to things that we have no access to with ordinary colliders. Okay? So this is something we're going to be discussing next time. Today I want to start by discussing quantum fluctuations of massless fields, zeta and gamma ij, that are produced during inflation. In that case, we're only going to be studying the free field limit of the theory, okay, which in fact we believe gives the dominant contribution to the signal. And then next time we're going to start discussing how to incorporate interactions and higher order correlations in these fluctuations. Okay, but this lecture today is just going to be about this first part. Okay, so let's start discussing quantum fluctuations. Is this a, sorry. Okay. Yeah, it's either enormously loud or I hear nothing. So, but okay, let's see. Okay, let me first give you a kind of heuristic for how we expect these quantum fluctuations in the inflaton field to generate fluctuations in density. And so for the time being, we're going to specialize to single field slow roll inflation. So inflation of kind of the simplest type, where we have a single real scalar field phi, called the inflaton. It has a potential v of phi. It has a flat region in the potential. And so the field is rolling down. The background value of the field, which is only time dependent, is rolling down this potential. And if the potential is sufficiently flat, and by flat we mean that the gradient of the potential, the first derivative, is much smaller than the height in Planck units, then that induces accelerated expansion. Okay? Famously, because effectively it acts like a cosmological constant, and a cosmological constant, of course, gives you acceleration. A second way of describing this period is in terms of the evolution of the Hubble parameter. So we can describe the evolution of the Hubble parameter in terms of this slow roll parameter epsilon. So minus h dot over h squared gives me a dimensionless ratio. And that describes the fractional change of the Hubble parameter in one expansion time. And so as long as that fractional change is small, you will satisfy the condition that you get accelerated expansion. In fact, you can algebraically show that these two conditions, this being smaller than 1, are just mathematically equivalent. Okay? So these are two ways of describing what I mean by inflation. And so in fact, I'm going to assume for this lecture that you have seen inflation before to save time. Okay? So we're going to immediately jump into the more interesting consequence of inflation, not the classical dynamics, but what happens if I now try to describe the system consistently in the context of quantum mechanics and general relativity. Okay? Before I go there, in fact, let me say two things about this epsilon parameter. So in this limit where the epsilon parameter is equal to 0, this limit corresponds to the zeta space. That corresponds to a perfect cosmological constant because h, the Hubble constant, is not varying. And h, as you know from the Friedmann equation, is related to energy density. And so if energy density is constant, you're describing the case of a perfect cosmological constant. So that's the zeta space. And the second thing to mention here is that inflation will end when this epsilon parameter at a certain field value phi e grows to be equal to 1. And at that moment, you get the end of inflation. And so in particular, in this potential here, this would correspond to some critical field value, say around there. Okay, when the potential steepens, the field accelerates, and the rate of change in the Hubble parameter becomes big, too big to sustain inflation. Okay, so the next thing we want to ask: what happens if we allow the field to fluctuate quantum mechanically? So instead of being a homogeneous field that rolls uniformly throughout space, you have small quantum fluctuations, delta phi. These fluctuations are now a function of space, so different regions in space probabilistically will have slightly different field values. So an immediate consequence of these fluctuations, so delta phi of t and x, is that different region of space will keep inflating longer and shorter. There will be variations in the time of the end of inflation, because the field value will take different amounts of time to reach this critical value phi e. So for example, a region of space that spontaneously fluctuated up the potential will keep inflating for a little bit longer. Okay? Regions of space where the field fluctuates down will terminate inflation earlier. So you get a fluctuation in the time at which inflation ends. Okay? But then after inflation ends, the field will oscillate around this minimum, and an oscillating field around the quadratic minimum acts like matter. So the matter region will dilute as a to the minus 3, while the region that keeps inflating will have constant energy density. So that's a dramatic difference. Okay, you have a very high energy density region that if it's still inflating, it keeps constant energy density. If it has terminated inflation, there will be a pocket of space that starts diluting very rapidly. Remember that the scale factor is still growing exponentially as the sorry, it's not. Take that back. In that region of space, of course, it has terminated inflation. So what that means is that very small quantum fluctuations in the field value delta phi through this switch here in the end of inflation can introduce relatively large density fluctuations delta rho. Okay? And we consider 10 to the minus 4 or 10 to the minus 5 enormous fluctuations relative to the fluctuations that the field experiences, which are governed by h bar. Okay? So you might ask, how can a small quantum mechanical effect generate macroscopically large size fluctuations? And it's through this switch in the time. and the fact that then different regions evolve dramatically different. And then in a certain gauge, we prefer to describe these density fluctuations in terms of the curvature perturbation zeta. Okay? So my goal for this lecture today is, in fact, to derive all of this rigorously. Okay? So that's why I said we have to do a little bit of work today. Okay, but before we go to the actual problem of interest, let me start by studying a slightly simpler problem. And so the simpler problem is to consider not fluctuations in the inflaton, but instead consider a massless free scalar field. And let me call this scalar field var phi. Later on, I'm going to be using var phi for the fluctuations in the inflaton, so you're going to recognize things as looking quite similar. And we want to consider this field in perfect de Sitter space. Okay? So in particular, what I'm ignoring for the time being is the way these fluctuations in the field interact with the background spacetime. So there will also have to be fluctuations in the metric, of course, when the inflaton fluctuates. And for the moment, we're going to be ignoring this. This is just a spectator field that doesn't have a large amount of stress energy, and so it doesn't really backreact on the metric. Okay? And so that will make certain things algebraically simpler, although all of the conceptual ideas about the quantization of the field are identical to what we have to do later. And so in fact, when we later study the actual problem, it's going to be very fast after we have been doing this. Okay, so to start, let's write down the action for this field. So of course, it's just the kinetic energy of the scalar field. With no potential. And let's evaluate that action in conformal time coordinates. So we use tau for time, d3x. This measure here, after going to conformal time, becomes an a squared. And then these derivatives here can be expanded into phi dot squared minus the gradient of phi squared. Okay? So now it turns out to be convenient, in fact, to absorb this factor of a squared into the field value, okay, by redefining the field, defining a new field, which is typically called v, as a times phi. That will canonically, that creates a canonical kinetic term for this field, this scalar field, okay. And that's of course useful for the quantization, because then we know that the conjugate momentum is just the usual usual velocity of the field. The price that I have to pay by doing this redefinition is that I will now get a mass term for the field phi, because the field A is time dependent. And so when I insert this into here, I pick up time derivatives of A from here. So what I find then is the following. So now I have a canonical kinetic term, the usual gradient. But now there's an effective mass that's given by the second derivative of the scale factor divided by A, v squared. Okay. And that's just the definition that I made. So of course these things are just equivalent. It's just a field redefinition. Okay. And the advantage of using v is that the kinetic term here doesn't have a prefactor that's time dependent. So that will help me for my quantization procedure. The drawback is that now it has an effective mass term, and this effective mass term is time dependent, and in fact it captures the entire content. If it wasn't for this mass term, this would just be a field of Minkowski space. So the entire expansion of the universe is in the fact that I have a time dependent effective mass of a field that effectively lives in Minkowski. So if you, instead of inflation, you had Minkowski with a time dependent mass that you somehow do engineering, that's what this is describing. In the case of inflation, of course, this mass term is very specific. We actually know what the scale factor as a function of time is for de Sitter. So this effective mass squared in de Sitter is just twice divided by conformal time squared. Okay, and so from now on, we're going to be using this specific value for the effective mass. So then I can write down an equation of motion for this field V. Each Fourier component of the field satisfies the following equation. So V double dot plus k squared minus 2 over tau squared, V of k, equals 0. And that equation is famous enough so that it has been given a name. So that's called the Mukhanov-Sasaki equation. Okay. One thing to immediately note about this equation is that if I go to very early times, and so very early times in terms of this conformal time coordinate during inflation corresponds to very large values and negative values of tau. So in the Sitter space, tau decreases, or like in magnitude decreases from negative infinity to 0 over the course of inflation. The end of inflation is as tau equals 0. So very early times, so at early times, and what I mean by early here is values of minus tau that are large enough so that they are larger than the inverse wave number. If that condition here is satisfied, then the gradient contribution here that will dominate over this effective mass term, and the field effectively acts like a massless field again, okay? And in particular, like a massless field in Minkowski. So in that particular limit, this becomes V double dot of k plus k squared vk approximately 0. Okay? And this, of course, you will all recognize just as the equation of a simple harmonic oscillator in flat space. Okay? And of course, this is a crucial feature of inflation because we know precisely what to do with a simple harmonic, I hope at least, quantum mechanically with a simple harmonic oscillator in flat space. Okay, maybe it's the only thing we know exactly how to do. Okay, and so this didn't have to be the case. You know, for a generic curved space-time, you know, you might not have had this flat space limit. During inflation, somehow it's guaranteed by the equivalence principle to work out this way, and this will allow us, in fact, later to pick a unique vacuum state for inflation and so on. So this feature of the equation is kind of crucial for this entire story. Okay, and in fact, it's the only subtlety that will appear later, that we're able to take this Minkowski limit continuously, and we're able to define the initial state of the fluctuations, the vacuum state, in this particular limit. Okay. Okay, so given that we have identified this now as a harmonic oscillator, let's just quantize it and look for the statistics of fluctuations in that quantized field. Okay, so just for completeness, I just want to go through these steps systematically. So what do we do, of course, when we quantize? We start with the classical fields and we promote them to operators. So the classical fields in this case are the field value V and its conjugate momentum pi. That's defined, of course, as the partial derivative of the Lagrangian with respect to V dot, which, because we have canonically normalized the field, is just V dot. Okay? And so we're going to promote these fields to operators V hat and pi hat. To make this then quantum mechanical, we impose commutation relations. So in particular, we're going to be considering equal time commutation relations. So in real space, this would be V of t and x commutated with pi of tau and x prime. And so this has to be proportional to I h bar, and then we're going to immediately set h bar to 1. So then I'm not going to be writing it. And it's proportional to a delta function of the difference between the two spatial locations. Okay? And this is just a signature of locality. Okay? So that if the 2 points are at separated points, they commute. The 2 operators are at separated points, they commute. Only there's a finite commutator only if the two are coincident points. And we can also write this as a commutator for the Fourier components. So v hat of k of tau pi of k prime of tau is equal to I 2 pi cubed in my Fourier convention delta of k plus k prime. Okay? Okay, so then the next step is to expand both of these operators v hat and pi in terms of its well, in terms of operators that describes its initial conditions. So we're going to be writing the following mode expansion. So the operator v of k, for example, is written as some time-dependent mode function times a hat of k plus complex conjugate of this first term to make a hat dagger of k. Sorry, it's a function of time. Okay, and so here I've actually used this. Sometimes people to make the distinction between the mode function and the operator that use different variables. Here I'm using the same variable. I'm only distinguishing them by the fact that the operator depends on the vector k, while the evolution component, the mode function here, only depends on the absolute value of the vector k. And so that's why I've been careful here to make this an absolute scalar. Okay, while here there's a vector k for the mode function. Okay, so in particular, any information about the direction of this Fourier mode is encoded in the initial conditions, which are given by this constant operators a hat. So this describes the initial condition. Well, this function of time here describes the evolution of those initial conditions. Okay? Well, because I can, in principle, or for a single mode, I can put a certain direction into the initial conditions. And it's just when you look at the evolution equation over there, you will see that the evolution equation just depends on the isotropic, so like on k squared, not on any direct vector. So the evolution doesn't know about directionality, and so it's only the initial conditions that can, in principle, be directionally dependent. And so in particular, should ask now, next thing we should ask is what determines this mode function. This mode function is just determined by the same Mukhanov-Sasaki equation that we had for the operator. Okay, so, sorry? Sorry, I didn't hear it. Yeah. This should not be there. Yeah. As I said, I claim to have been careful and I wasn't. Yeah. Okay. Yeah, of course. So the reason these mode functions don't have directionality is because when you look at this Mukhanov-Sasaki equation here that they have to satisfy, there's no information about direction in these equations. Okay. And so solution to those equations will be a function of the absolute value of k. Okay. So these mode functions have to satisfy the equation of motion, and then in addition we're going to impose that they satisfy a certain normalization condition. So in particular the amplitude of the mode function times the complex conjugate of its velocity minus the velocity times the complex conjugate of the amplitude. This particular combination here, we're going to define this combination to be I. Okay? This is not good. Sorry? Where is it? Oh, I've just written the Fourier mode here, and you could do the Fourier transform of this Fourier mode if you wanted to get v of x in real space. It's the integral over k, this mode, e to the ikx. Okay. So yeah, I've done that implicitly. Okay, so let me go over here. so why did we choose this particular normalization condition? The reason we chose this is it's easy to see that if you take this mode expansion, substitute it into this commutator here, you'll get a very familiar looking commutator for this operator A hat. Okay, and that's precisely because of this normalization condition. So you can check for yourself that the commutator of A hat of K, A hat dagger of K prime is essentially just the delta function with an extra 2 pi cubed. Okay, and so the commutator of these initial conditions operators has been normalized appropriately so that I can interpret this guy as a creation operator and this guy as an annihilation operator. Okay, and then of course I can do the usual thing and then define a vacuum state as a state that's annihilated by this guy. So define okay. So this is going to be our vacuum. Okay, so I hope so far this has been no super basic. Okay, and so now I want to discuss a little bit the only subtlety in this calculation. So far it really was just harmonic oscillator. Okay, so the only subtlety comes about because I've so far only specified. So this is a second order differential equation. In principle, it has 2 solutions and 2 integration constants, but I've only specified 1 condition on this mode function. So as we will see in a moment, we still have a 1-parameter family of solutions to this equation. And that means I can make a change, I have 1-parameter freedom to make a change in this mode function and make a simultaneous change in these initial conditions operators while keeping the operator solution fixed. Okay, but if I'm allowed to still change the meaning of the operator A hat, it also means that I'm intrinsically changing the meaning of the vacuum state 0. So the vacuum is not yet at this moment in time specified uniquely. Okay, and so we will have to deal with this now. Okay, so let's spend a little bit of time talking about the choice of the vacuum. So let me tell you what the most general solution to the equation of motion is. So the most general solution of the Mukhanov-Sasaki equation takes the following form. So there's an integration constant C1, 1 minus I over k tau, e to the minus I k tau, plus C2, 1 plus I over k tau, e to the I k tau. Okay? Where these 2 complex constants here have to satisfy the constraint that the square of the first one minus the square of the second one is equal to 1 over 2k. Okay? So I leave it to you to show that, first of all, these 2 functions by themselves each solve the Mukhanov-Sasaki equation. Okay? And then if you want to set that this mode function here satisfies this Wronskian normalization that I wrote over there, you get this constraint on these 2 constants of integration. Okay? But we, as I advertised, given this, we still have a 1-parameter family of solutions given by this equation with this constraint. Okay. So how do we impose an additional condition to fix this ambiguity? So to fix v of k, and hence to specify the unique vacuum, we do what? What do you think we should do? Yes. What? Yes. Yeah. And what's special about the vacuum? What type of vacuum do you specify for the harmonic oscillator? But what physical condition do you impose on a state being the vacuum state? What's special about the vacuum state? Sorry? Minimal energy. Okay. So we'd like to have this thing to reduce at very early times to the minimal energy state. And so for that, we're going to consider the limit of very early times. So that's during inflation, that's tau going to minus infinity, of the expectation value of the Hamiltonian in the state 0, okay, that I'm proposing to be the vacuum state. Okay. So I've written out the details in my notes. I'm not going to go through them. So what I show in the notes is if you take this mode function with this constraint, substitute it into the Hamiltonian, you'll get an expression for this in terms of C1 and C2 subject to this constraint. And you can minimize that condition. You can ask that that's the minimum energy configuration. So when you do this, you will find that this is minimized if the absolute value of C1 is equal to 1 over square root of 2k. There's an irrelevant undetermined phase of this constant. And the second constant here is 0. Okay? So it means you have to pick this part of the solution and not allowed to mix it with any amount of this part of the solution. Okay? And so this is also called the positive frequency contribution because it has a negative sign. Okay? And you can check other things. For example, if you take this mode function then and substitute it into here, in the early time limit, the minimum energy state will have the usual 1/2 h bar omega that you recognize from the ground state of a harmonic oscillator. Okay. So all things will start to look familiar if you make this choice of mode function, and it will look different. It would generate an excited state if I had some finite value for C2. Okay. So you can check that for yourself. So through this condition, we have obtained a unique mode function called the Bunch-Davies mode function. And so let me just write it out explicitly because this is going to be the basis for everything we're going to be doing in the following. So the unique mode function that we determined has a normalization that's 1 over square root of k up front. This should also be familiar from the harmonic oscillator. E to the minus ik tau. Okay. But this mode function now carries all the information about the statistics of the field. So we can now go and start calculating whatever we want. The mean value of the operator, the variance of the operator in either a vacuum or an excited state, and all those kind of things, given that we have this mode function available. Okay. So in particular, the statistics that we're going to be interested in is the variance of the field. Okay. So it's easy to show that the expectation value will vanish. And so the next interesting moment of the operator is the square. And so that's what we want to calculate now. And we want to calculate that in the vacuum state. So in the vacuum state, in fact, these moments are called 0-point fluctuations. Okay, so as I mentioned, this expectation value would vanish. Okay, of course, if I'm expanding this operator here into creation annihilation operator linearly, annihilation operator would act here to annihilate this expectation value. Annihilation operator would act here to annihilate it, and you get 0. Okay, so the next interesting thing to look at that's not vanishing is the expectation value of the operator at some time tau, position x, correlated with a second one of these operators at the same time tau. And now in principle, I could be choosing a different position x prime, okay? But let's just do it at the same location for simplicity. I'll leave it to you as an exercise to check what changes if I'm choosing x and x prime in this correlator. So if you substitute what we have determined so far, namely the mode expansion, and then in terms of the mode functions and the creation and annihilation operators, what you will find after a few lines of algebra is an integral over momentum k times k cubed over 2 pi squared, absolute value of the mode function squared. Okay? And so now I can finally explain why. Remember when we were writing the dimensionless power spectrum, I was always writing this as 2 pi squared over k cubed. Yeah? This is where the 2 pi squared comes from. Okay? Because this particular integral is the logarithmic integral over the dimensionless power spectrum of the variable v. Okay? So what we had identified here is the dimensionless power spectrum. So there's a relationship between the variance of the field in real space and the integral over momenta of the power spectrum. Okay? And so the other thing you notice is that there's a very simple relationship also between the power spectrum and the mode function, okay, of this mode expansion. Namely, just the square of the mode function essentially determines the power spectrum. Okay? And given that we know what the mode function is, we can calculate the power spectrum immediately. And that's the final thing we want to do. Okay? So for the Bunch-Davies mode function, we find the following result. So let's in fact go back to our original field phi. This is related to the power spectrum of the variable v dividing by a squared of tau, where in the zeta space a of tau is minus 1 over h tau, where h is the Hubble parameter in real space. Okay. So all I have to do is take the Bunch-Davies mode function from over there, substitute it into here, take its square, and see what you get when you also substitute the scale factor in the zeta space. And so what you should be finding is h over 2 pi squared times 1 plus k times tau squared. Okay, I'll leave it to you to check that that's true. And so now if I take the superhorizon limit of this expression, superhorizon limit corresponds to very small k's, or for fixed k it corresponds to late times, small tau. So the combination k times tau is what's invariant, and so I'm going to send that combination to 0. And so when I'm sending that to 0, I'm left with h over 2 pi squared. Okay? So if you have never seen this before, you should celebrate it. Okay? It's a very famous result. These are the Gibbons-Hawking kind of fluctuations in the zeta space. They're scaling with the cosmological constant determining the zeta space, which sets the Hubble rate. And there's a famous 2 pi here. Okay? So that sets the size of the power spectrum of quantum fluctuations of a spectator field in the zeta space. Another thing to notice about this result is that, first of all, since we are in the zeta space, this h is just a constant. So this means that this power spectrum here is a constant independent of momentum. So these fluctuations here are scale invariant. And they're scale invariant because we are in the zeta space where there's no time dependence and no real scale associated with the physics. Okay. So this is also a good starting point, of course, because later we want to generate scale invariance in the zeta fluctuations. And so starting from a condition where we have exact scale invariance and then slightly breaking it will bring us to the promised land. Okay.
Okay.
Any questions about this? Yeah.
So
So a conformally coupled field, of course, doesn't know that it's living in the zeta space, so it will not receive these large fluctuations. So it will just get the usual Minkowski space fluctuations, but it will not have this feature that the fluctuations get amplified when they cross the horizon. Okay. So that answers, for example, the question about whether photons receive quantum fluctuations during inflation, which are also massless fields. But photon fields typically are conformally coupled, and so therefore you don't expect quantum fluctuations in the photon. Okay. Yeah.
So do you need to impose some sort of momentum cutoff, or that's irrelevant?
At high momenta, you mean, or low momenta? Yeah. So the issue is actually at both high and low momenta. Okay. In particular, there are thorny issues, specifically when you're working in this idealization of the zeta space. There's a whole community of people that does that for a living, of arguing about what happens in the IR. You know, there are logs that kind of could accumulate or not when you calculate loops and so on in the IR. And in the UV also, you might worry about what happens at, you have to regulate the theory at very high momenta. There's something called the Trans-Plancking problem that some people are terribly obsessed about when the momentum gets very high and they think they have no control over this. But okay. Yeah, it's a bit strange to, let me just say it this way. It's a bit strange to worry about this because, of course, at very high momenta, we're approaching flat space. And so if we're worried about these kind of things, then we should be worrying about our flat space QFT more than something like that. Okay. Any other questions? So yeah, really the high momentum limit is the UV limit where we should be regulating things just the way we do it in a flat space, and we can do that. You might worry, for example, about this limit that I took here. What do I mean by tau going to minus infinity? That also corresponds to infinite momenta and infinitely early times. Okay. What I really mean is that I can do the same procedure of picking this vacuum state adiabatically. So because inside of the horizon things are evolving adiabatically, and I can choose adiabatically as a changing function in time always the ground state. Okay, but it will be shifting adiabatically. Okay, so there's something called the adiabatic vacuum, which is actually the same as the Bunch-Davies vacuum, but it's a slightly more sensical way of defining things without having to take this limit of going to minus infinity in time. Okay. Any other question? So let me also just tell you what would have happened if I had chosen this field phi to have a mass and not be a massless field. And the reason I want to tell you a couple of results about a massive field in the zeta space is because it's going to be useful later, or tomorrow, in fact. So for a massive field, we would have found the following Bunch-Davies mode function. So it works exactly the same way, because if I go back to very early times, I'm still reaching the flat space limit, because at very high momenta, early times, the momentum dominates, and I can go to sufficiently high momenta or small scales that the mass term becomes irrelevant. So I would be changing so if I had a mass, I would have to add an m squared a squared here, okay? But I can a decreases, okay? And so if I go to sufficiently early times, m squared times a is small. In particular, it's small relative to k squared, and I'm still reaching the flat space limit. So it doesn't change the Bunch-Davies initial condition. But the mass of the field does change how this initial condition evolves further in time. And I get a new mode function that is slightly more complicated than the one I wrote previously. So I get some kind of annoying factors up front, so square root of pi over 2, a square root of minus tau, e to the I 2 nu plus 1 pi over 4, where this nu here is a function of the mass. Nu squared is equal to 9 over 4 minus m squared over h squared. And then the whole thing gets multiplied by a Hankel function of degree nu of the first order minus k tau. Okay? you can check for yourself that if you take the early time limit, so very large negative tau of this expression, you reduce to the right limits for the vacuum state of a harmonic oscillator. But I'm not going to be doing this for now. Let me just describe certain limits of this mode function. So in particular, if I take the mass to be smaller than 3 over 2h, so somehow 3 over 2h is special, and things will evolve differently whether the mass is smaller than 3 over 2h or bigger than 3 over 2h. And so whether a field is light or heavy during inflation is determined by this condition. So in particular, if I choose it to satisfy this inequality, you will see that this variable nu here is real. And when this variable nu here is real, then you will also see that this factor here is just an arbitrary phase that will disappear when I take a square of this mode function. So this factor doesn't matter. And we would find that the power spectrum of the field phi, and let me immediately take the limit, superhorizon limit of k tau going to 0. We have again find h over 2 pi squared. But now in addition we find a time-dependent contribution, k times tau to the power 3/2 minus nu. Okay? And so there's a time-dependent contribution and momentum-dependent contribution that does depend on the mass of the field. And so in particular, this contribution here means that this power spectrum now is not scale invariant. Okay? So it's not scale invariant. In particular, it's conventional to define a spectral index, just like we had last time, as the derivative of the log of the power spectrum with respect to the log of the wave number k. Applying this to here, we will find that this is 3/2 minus nu in the limit where m is much smaller than h. This becomes 1/3 m squared over h squared. Okay? So you see that the amount of deviation from scale invariant is controlled by the size of the mass in units of the Hubble scale. And in particular, if they take the limit where the field becomes massless, we produce scale invariance, as I showed. Okay? But the larger I make the mass relative to Hubble, the more I'm deviating from scale invariance. And for masses of order the Hubble scale, I get kind of order 1 deviations from scale invariance. Okay? Okay, so then let's just see what happens if I pick larger masses. So if I choose the mass to be larger than 3/2 h, then the parameter nu becomes imaginary. And let me redefine it as I times a new parameter mu, which is real. Okay. And in fact, in the limit m much greater than h, this parameter mu is nothing but the ratio of mass to Hubble scale. So it's I times mass over Hubble. Okay. And so in this limit, you can check from this mode function solution that we would find that this power spectrum now receives an exponential suppression. So e to the minus pi mu, or in this limit here, it's e to the minus pi m over h. Okay? And this exponential suppression here arises from what was previously an irrelevant phase factor. Yeah, in the case where nu is real, this was an irrelevant phase, and I could drop it because it never appears in any observable. But now this phase factor, I times an imaginary number, becomes real, and I get this exponential suppression of the power spectrum. Okay? So what this is telling us is that the production of very massive particles with masses much, much bigger than the Hubble scale is exponentially suppressed. And sometimes this is called a Boltzmann suppression, because if you use some kind of thermal interpretation of this procedure in de Sitter space. Okay? Is that clear? Any questions? Yeah?
So this phi is the same as the spectral index 2 days ago?
Almost, except here I've defined it more sensibly. So the spectral index last time was ns minus 1. And I fear I've not done the minus 1 craziness. Okay. just because I can, because this thing doesn't have a special meaning. Okay, but yeah, morally it's the same. Yeah, I've defined it in such a way that n phi equals to 0 corresponds to scale invariance.
So this corresponds into pair production.
Yeah, you can think of it that way, exactly. And that pair production is just exponentially suppressed. Okay. Okay. Any other questions? Okay, so far we have idealized things a little bit by considering spectator fields in de Sitter space. So now I just want to sketch for you what happens when you drop this and actually look at inflaton fluctuations and how they backreact on the metric and so on. And I'm going to do that part kind of much less so all of the technical work we have done. Okay, so conceptually nothing new will happen here. There will just be a little bit of technical complication, and most of that is buried in my notes rather than I'm not going to be writing it out in detail. So let me just highlight some of the things that happen when you look at fluctuations during inflation. So now what we want to consider is fluctuations in the inflaton field phi. So meaning the difference between the field value and its homogeneous background. So, okay. But it wouldn't be consistent just to focus on these fluctuations. We also have to consider fluctuations in the metric G mu, because there are Einstein equations that are related to, and so it wouldn't be a consistent solution just to look at fluctuations in the inflaton field. So what we have to do is we have to take the full perturbed metric and subtract from it the homogeneous FOW part. And so we'd like to solve the system of the coupled equations between delta phi in the matter sector and delta G mu in the gravity sector. Okay. And you can do this multiple different ways depending on the gauges and depending on how hard you want to make your life. So I want to pick the following gauge. So we're going to be using co-moving gauge. So co-moving gauge is the gauge where I make a redefinition of time to remove this inflaton fluctuations delta phi. So if somebody handed you an arbitrary gauge, chances would be there would be a fluctuation in the inflaton field delta phi, but you can always redefine your time slicing in just such a way that it removes this particular fluctuation. And so you're co-moving with the inflaton field. So this picture that I had earlier when I said the inflaton field was rolling down homogeneously and we had small quantum fluctuations that led to a time delay, that picture actually is gauge dependent. Okay, so I'm now picking a gauge where this picture is maximally far away from that picture. So I don't really have a time delay in the same sense, but I directly have curvature perturbations during inflation. Okay, so that's the slight shift in your head that you have to make. So when you make this kind of gauge choice, you have moved all of the fluctuations in the metric. So in particular, the Gij part of the metric is a squared 1 plus twice the curvature perturbation zeta, delta ij. And then I can also add for a tensor contribution if I want to study gravitational waves later. Okay. This 1 plus 2 epsilon is what we previously had. Previously, I think I was writing this as e to the twice zeta, e to the twice zeta. That's the nonlinear generalization of this. I have linearized already this metric component when I'm writing it like this. Okay. So this metric fluctuation has two components. The usual scalar component, which was the curvature perturbation that we have studied previously, and now there's also a tensor part, which I'm going to mention later, which will parameterize gravitational waves. But that's just the spatial part of the metric. There's also the temporal part and the off-diagonal piece, which has G0 and I, because it has fluctuations, so it doesn't have to be isotropic. And this part is not dynamical, but can be chosen, but is a function of zeta itself. Okay. So in particular, this relationship between these metric fluctuations and zeta is determined by the Einstein equations. In fact, there's a very beautiful formalism called the ADM formalism that allows to describe these additional metric perturbations in a very convenient way. Okay. So in my notes, I define the ADM formalism. I derive for you the constraints. I show how they relate to zeta and how you can solve and plug back into the action. Okay. And basically, I'm following a beautiful paper by Juan from some time ago. Okay. In fact, if you want to learn about this calculation, even the calculation that I showed earlier, his paper is actually still one of the nicest description of this. Okay. And then it also includes how to talk about interactions, which we're going to be doing next time. So I'm going to spare you all of this. Is really kind of hard work. Okay, solving the constraints and then plugging them back into the action and so on. That actually takes work. Okay. And you usually wouldn't do it. You wouldn't be doing it by hand. If anybody wants, I can send you a Mathematica code for doing this. Okay. Maybe once in your life you should do it by hand, and then the next time you will not do it. Especially if you then want to go to higher orders and so on, it becomes a nightmare. Okay. But conceptually, what you have to do is you have to take the complete action for the coupled graviton-inflaton system. So for gravity, you have the Einstein-Hilbert piece. For the inflaton, we have the slow roll action. Okay. And so now we want to perturb this, okay, and expand to second order. And when you do this carefully, what you find is the following. So the second order action for the field zeta is a squared, is the usual measure factor that we always get, times the slow roll parameter epsilon, zeta dot squared minus the gradient of zeta. Okay? So in fact, one minor miracle here happened, okay, which is important to appreciate. So one thing that happened is that this zeta field doesn't have a mass term, okay? But when you do expand this naively, you'll get a lot of mass terms, okay? And you have to be careful that these mass terms all cancel, okay? And they have to cancel because otherwise Weinberg would be wrong, and that never happens, we know. Weinberg would be wrong to claim that zeta is conserved outside of the horizon. As we saw actually in the power spectrum for the massive field in the zeta, you saw it had a time dependence even at late times. So it was actually decaying outside of the horizon. If zeta had an effective mass term, it would also be decaying outside of the horizon, and that's not allowed by our theorem. Okay? And this is just a specific case of the more general theorem, and we're finding it explicitly verified here. But this zeta doesn't have a mass term, so if you look at its mode function and ask what it does at late times, it will freeze. And it wouldn't be freezing if it had a mass. This epsilon here is the epsilon that I introduced at the very beginning as my definition. It's this combination, okay? And in fact, it's this combination in general, but then for the scalar field case, it's 1/2 phi dot squared divided by m Planck squared h squared, okay? Epsilon is small means inflation, meaning that the ratio of kinetic energy to total energy is small. That's why we call it slow roll in the first place. Okay, so that's but this epsilon will just appear when you expand this from here, for example, and using the background equations of motions and so on. So you have to do some work. Okay, so I'm making this sound very simple. Okay, this from step here to step here, but it's if you were to write out the algebra, it's pages of algebra. Okay. Okay. But that's kind of nice now, because if we look at this, you will see that this is exactly what we had before, except for this epsilon here. Okay? So the only thing really that changed from the case where we had a massless field in the zeta space is we have an extra epsilon. Okay. So it really just changes the normalization of the field, which is important because the normalization of the field will determine how big of a size of fluctuations I have. In particular, for example, if this epsilon here is 0, I in fact get infinitely large fluctuations for zeta, because the field here. And so let's actually see this. So the quantization, once you get to this point, proceeds exactly as before. So we're not going to be doing it again. And when you go through it, it gives the following final answer. The dimensionless power spectrum for zeta as a function of k and of time in the super horizon limit k tau going to 0 is h over 2 pi, like before. Notice h, I'm allowing it to vary in time because we're not in perfect de Sitter space anymore, squared. Then an extra 1 over epsilon, which is can also be a weak function of time. That 1 over epsilon comes precisely from this. Yeah? If I defined a new canonically normalized field and doing that definition, then that canonically normalized field has the usual quantum fluctuations, and that field redefinition appears here in the 1 over epsilon. Okay. And in fact, it's this 1 over epsilon here that signals what I just mentioned earlier, that if I'm choosing epsilon to be 0, I get infinitely large fluctuations. Okay. But that also kind of makes sense, because in the limit epsilon going to 0, the meaning of zeta becomes a pure gauge mode. And this infinity of the correlation function signals to you that zeta is actually not physical anymore. Yeah.
So inflation ends at epsilon equal to 1.
Yeah. Sorry, for eps?
So if I look at this action and I put epsilon equal to 1, which is when
yes.
I get over the zeta, which looks
well, but it's a different variable. It's zeta, it's not the canonically normalized field V that we had previously. Actually, it's a good question, but maybe in the interest of time, let's discuss it later. Okay. Okay. In fact, this is not the complete answer yet. There's still also a time-dependent contribution, k times tau, minus 2 epsilon minus eta, where eta parameterizes the time variation of this parameter epsilon. So this is in fact the fractional change of epsilon per 1 expansion time. And typically this also has to be small during inflation in order for inflation to last. We have 2 conditions, okay? I didn't talk about this so far. And so actually, in the notes I show you that this particular combination here, in fact, despite appearance, despite the time here and time here and time here, is actually constant, it's time independent. And in particular, this time dependence here is exactly necessary in order to cancel the time dependence that's living inside of h and the time dependence that's living inside of epsilon. So you can check that this is actually constant, although I have several time dependencies here that have to precisely cancel. And they had to cancel because I actually, just looking at the mode function, I saw that zeta was freezing, and so at late times I need to get a time-independent answer. And these combinations work out exactly in that way. Okay? There was some question. Yeah? Yeah, if epsilon were to vary very fast, then you can get non-adiabatic particle production, not just at the horizon, but at the scale given by the time variation of epsilon. So if epsilon varies on a time scale that's faster than the Hubble expansion time scale, then you have a new scale in the problem, which is that the effective mass of the... So this effective mass that we had was varying on a Hubble time scale in the usual case. Now if this effective mass varies faster than that, you have an additional source of energy in some sense, not just the expansion of the scale factor, okay? And that can lead to additional particle production. It would change the answer. Yeah, that's sometimes what you get when you have features in the potential and those kind of things. That will lead to changes to this. So yeah, we have assumed slow roll in all parameters. All parameters are slowly varying over Hubble time. Okay. So this is nice. So this is a famous result, of course. This is the main result that we're testing against observations when we look at the CMB spectrum, because that's the input that we took last time to evolve it forward in time. Okay, but now we're we justified why we got some nearly scale invariant input. Okay. However, we do see here, we see a k-dependence, and that k-dependence survives. There's nothing here that can cancel that k-dependence. Okay. So this spectrum, in fact, is not exactly scale invariance. So it has a small deviation from scale invariance. So the predicted deviation from scale invariance is this combination ns minus 1 that we had last time. It's defined as the logarithmic derivative of the power spectrum with respect to k. And this derivative will just pick out the exponent here of this power law. And so what you find is you expect this to be minus twice of epsilon minus eta. Okay? So there are two sources of deviation from scale invariance. There's one, the spectrum is not scale invariant because h is not constant, so epsilon is finite. And epsilon itself can vary, so eta is finite. Okay, so there are these two sources of scale invariance. But both of these sources of scale deviations from scale invariance have to be smaller than 1 in order to sustain slow roll expansion. Okay, so we predict two things. We predict that it's not exactly scale invariance, but not by a large amount, just by a small amount. Okay, and the typical values for these things would be 1 over the number of e-foldings or things like that. So we expect percent level deviations from scale invariance. Okay. So the rather fantastic thing was, of course, that this deviation from scale invariance has been observed. So the measured value of this combination ns minus 1 is minus 0.04 plus or minus 0.01. Okay. So this is the first and best hint that we have that whatever created the initial conditions had some dynamical origin to it. Okay, and in the context of inflation, that dynamics becomes very concrete. All right. Yeah.
Maybe it's a stupid question. At what time is this evaluated?
Well, very good, very good. Yeah. So this is evaluated. I should have maybe made this clearer. At some fiducial time that you pick. So you remember that when we were defining this, we were defining it as as k over k star ns minus 1, where k was some reference scale relative to which I defined the amplitude and the spectral index. If I change my reference scale, I will change as and ns, but in a predictable way. Yeah, and so here it's the same. So I'm choosing some specific time during inflation, for example, when some particular mode that I care about to represent this pivot or reference scale, when that mode exited the horizon, and I'm evaluating the slow roll parameters at that time. Okay, and I could choose a different. I just have to make sure that I do that consistently. So whatever I'm choosing here for my reference scale will give me information about the mode that crosses the horizon at some certain time during inflation. Changing that time would change the meaning of this reference scale. Okay. But that's just what you have to do. If you want to define some small power law deviation, you have to define relative to what reference scale I have to do that. Yeah. Why doesn't tell us that? Yeah, so what would be proof that inflation was true? Proof that inflation was a bit hard. So notice that one thing is that we're not measuring epsilon. Yeah. One nice thing would be to know the value of epsilon of some kind of FRW expansion and showing that to be small, because that's the definition of inflation. But there's a degeneracy between epsilon and eta here. So we're actually only measuring a combination of the two. Okay. And by measuring the amplitude, I'm also measuring a combination of epsilon and h. So also that measurement of the amplitude also doesn't give me access to just epsilon and being able to prove that it's smaller than 1. The other argument against this being proof maybe also is that So scale invariance somehow is very natural. You could imagine other mechanisms generating scale invariance. And so then weakly breaking scale invariance maybe is the next natural thing. Okay? So if you had to put yourself into some place of k dependence of the spectrum, maybe, and this in fact how historically what people did is they said, what if the fluctuations were just distributed perfectly scale invariant? It's called the Harrison-Sedlowitz spectrum. And that actually came before inflation. Yeah? And then, weakly breaking it and so on, you could imagine some other mechanism doing that. Okay? What's special about inflation, in fact, okay, there's a theorem that I would like to prove. I've never managed to prove, but maybe as an exercise for you guys. So what's also special about inflation is that it produces very nearly scale invariance, but also very Gaussian. And so the combination of the fluctuations being nearly Gaussian in scale invariance might be a hint. Yeah? So because actually we often know scale invariant theories, and then when you want to break that scale invariance, you do that through interactions, like loop corrections to the scale invariant conditions. And those interactions have to be sufficiently large, and that would create also interactions that you would see, and it would be not Gaussian. So inflation does something quite special, that it's nearly scale invariant and also very weakly interacting. And maybe some condensed matter people could tell me whether that is a natural condition to expect in systems that exhibit scale invariance or not. But yeah. But my feeling somehow is that often when I break scale invariance, I'm doing that through kind of loops that carry information about interactions, and it wouldn't be Gaussian anymore. Okay. So the slogan would be that inflation produces something that's more Gaussian than scale invariant, and I typically expect the opposite. And so I'd like to prove the theorem that means something strong. Okay, but I've never managed to. Okay. Okay, 2 minutes, yeah. So then maybe I just use words. So the very last thing I would have done if I had a little bit more time, but it's not essential, is talk about the calculation for this tensor component here. That calculation, in fact, is even simpler than the one for zeta. The reason it's simpler is that there's less mixing going on, because this is a tensor component, and so you don't have to worry about at linear order tensors, scalars, and vectors decouple. Tensors, in fact, are gauge invariant, so you don't have to worry about gauges. So a lot of things are just simpler. There's, in fact, no epsilon in the action when you derive the quadratic action for this gamma ij. This action is just normalized by the Planck scale of the Einstein-Hilbert term. If you expand that to second order in gamma ij, you'll get just m Planck squared over 8 or something, times the flat space with an a squared, the usual a squared, but no epsilon. Okay? So what this means is that the quantization of this one actually proceeds exactly like that for a massless field in flat space, or in the zeta space. Okay? Just 2 copies of that because there are 2 polarization modes for this gamma ij. And so you will get a power spectrum for gamma, which is 8 over m Planck squared times h over 2 pi squared, and then minus k times tau minus 2 epsilon. Okay? So you see, in this case, it's similar to what we had before, just the 1 over epsilon is missing because that doesn't appear when you quadratically expand Einstein-Hilbert. Okay? And then if Igor gives me 1 minute, I'm just going to mention that what people like to do instead of actually quantifying this tensor power spectrum, they take the ratio of the power spectrum of tensors at some reference scale to the power spectrum of scalars at some reference scales. That's an equally good measure of the power spectrum of tensors, of course, because the power spectrum of scalars has been measured. So this is just dividing out the 10 to the minus 10 that normalizes the scalars, so we get some more reasonable sized number for the ratio. And in fact, if we look at these expressions, what you would find is that the ratio of these two is 16 times epsilon. Okay? And that maybe answers also one of the questions that we had earlier, that it would be nice to measure epsilon separately from everything else. And measuring the tensor to scalar ratio, in fact, would allow us precisely that measurement. It would tell us epsilon, and if we found it to be smaller than 1, it would be good evidence for something. And plus, the excitation of gravitons during inflation is somehow the simplest process that can occur. So seeing that graviton background created by inflation would be very, very convincing. Okay. So then just finally, what's the current status. Currently, constraints are often presented as constraint on the combination of R and NS, scale invariance corresponding to NS equals 1. And so the exclusion contours look something like this. Everything outside of these contours is ruled out. Everything inside of these contours is favored. So in particular, what's being ruled out is lambda phi to the fourth cannot be the potential of inflation. M squared phi squared, unfortunately, cannot be the inflaton potential. M squared phi squared would have been beautiful. It just has one free parameter. That free parameter is fixed by the amplitude of zeta fluctuations. Everything else is then predicted. R and NS would be predicted. So you have one parameter and you would predict 4 things. Okay. Unfortunately, it was too predictive, and so it's has been ruled out. So you have to look deeper into the space of inflationary models in here. Okay, so let me stop there.
These models are very transplain.
Exactly. Yeah. So there's a special feature where you will see in my notes derived that models that have sufficiently large amplitude for this tensor to scalar ratio, bigger than about 1%, okay, involve field variations that are larger than the Planck scale, okay, and so that makes some people very nervous. Some people makes it curious. Some love it. Some hate it, okay. But at the moment, experiment is deciding, okay, and it's digging deeper and deeper into the regime where you not have to do super Planckian variations. Yeah.
Some people talk about R squared.
Exactly. R squared lives around here. No, it's like the best. Okay. Exactly. Yeah. So what R squared actually means is it's R plus M squared R squared, or some scale. Let's see, because we have M Planck. So I think if you write it like this, okay, you have to, of course, to make the right dimensions, you have to put a scale here. And indeed, the scale has to be picked to be enormous. So there's a similar super Planckian problem. For
M is much bigger than M.
Well, my bigger worry actually is that this M here is much bigger than H. And so because R during inflation is Hubble squared, and so so you worry about, somehow you can't think of this as an expansion. So what about the M to the fourth R cubed that has been dropped here? You shouldn't be thinking. This is telling you somehow you should not be thinking about it that way, but nobody has given me a replacement of how to think of it otherwise. So it's. I think it comes to what Juan was saying last time about effective field theories, that you shouldn't truncate it and then solve for the truncated version without thinking of this perturbatively. In order for this to be inflation, this has to be not a perturbative correction to R, but something that's of the same order of R. Yeah, and so we can't. This is not the usual way of thinking about effective field theory. Yeah.
So if I believe in grand unified theories and also inflation, I want inflation energy scale to be higher than the gas.
Yeah.
To solve the monopoly problem. So below.
Yeah. Yeah.
Solve the monopoly problem.
Well, inflation. Well.
First, I produce monopoles taking the SU5.
Okay.
And
Yeah.
then I dilute them with inflation.
Sure.
Because I did in a boundary next one.
Yes, because R, in particular, measuring R carries a lot of information. It in particular also carries information about the energy scale of inflation. Because it allows us to measure epsilon, and we have measured this combination epsilon and H through the size of the scalar fluctuations. So knowing epsilon would then immediately also tells us what H is, and H is related to the energy scale of inflation. So we could actually decide the question whether inflation happens close to the grand unified scale or at much lower scales. It then turns out that if you want to see tensors ever in your life, okay, it has to be very close to the grand unified scale. And if that were to happen, that we see tensors, then I think it would encourage people to think more closely about the connection between grand unified physics and inflation, because it has somehow nailed down that inflation was an effect that's close to the grand unified scale, so maybe there's a connection between the two. Okay, so yeah. Not fluctuations, or if the classical valve of the field was larger than Planck scale. Actually, it's not just larger, but it moves over a distance that is large. Okay. So, for example, in M squared phi squared, the field has to start off very far from the minimum at about 15 times the Planck scale, and then rolls down to square root of 2 times the Planck scale when inflation ends. Okay, so that's 15 Planck units that it varies. And so now the problem is, if you take m squared phi squared and ask, let me write down corrections to m squared phi squared in an effective field theory that are polynomial in the field phi, suppressed by some new scale lambda. If the field phi, say phi to the fourth over lambda, then if the field phi moves by a large distance, larger than the Planck scale, the only in order to suppress that correction, you have to choose the cutoff scale lambda to be super duper Planckian. But you typically don't want to do that. You think the effective field theory breaks down before you hit the Planck scale. And so making that assumption, you would say that you have an infinite series of corrections that all become simultaneously important. And that's why people worry. The way out that people consider is to say that the field theory is not generic in the sense, but has an additional symmetry that forbids all of these corrections. And that symmetry would only be broken by the m squared phi squared mass term. Imagine that you had a theory that in the absence of the mass, like an axion, in the absence, or a perfect Goldstone boson, in the absence of this mass term, it's perfectly shift symmetric, has just a cosmological constant term. And then you add the mass term to break that symmetry, but you still use the fact that the symmetry is broken weakly by the mass term to control all radiative corrections, because they will all have to scale. Any loop correction will have to scale proportionally to the breaking parameter, which is the mass itself. So you can technically naturally make it stable. Okay, it's just a problem of UV completion. Where did this come from, and what protected the symmetry, and so on. Especially since there's law in quantum gravity that there are no global symmetries in quantum gravity, and so you have to ask about breaking of those symmetries, and then you have to ensure that the breaking of these symmetries that you expect is weak enough to allow everything to be stable. Okay, all right.